Okay. So, okay. So I think this is now getting broadcast on Google Hangouts. So the job in this PD is to generate the abstract syntax tree. So let me just show you an example. Maybe I should make the font bigger first. Is it visible now? Okay. Okay. So don't worry about the numerous amount of files in here. The important file is only one, which is example2.g4. Okay. So let me also make the font here bigger. Okay, so let's just run example2.g4 and see what happens. Run. Okay, so I gave it some random test input, and ANTLR automatically generates the parse tree, as you can see in the picture. But this is not the tree that we want. We really want the abstract syntax tree. Okay, so so how to get the abstract syntax tree? Let's see that. So instead, so here, if you have noticed, in addition to generating the parse tree, I have also printed out some lines over here. So these lines are really going to print your abstract syntax tree. That's what's going to happen. This is a textual description of the abstract syntax tree in the dot language, these lines that I have printed out. So I'll just divert these lines into a particular file. Okay, let's do that. Okay, so I'm just adding this redirection sign and then test dot dot. Same parse tree appears, but those lines don't appear anymore. They are being written to test dot dot. Okay. So let's see what was in test dot dot. So here is, this is the content of test dot dot. Basically, it says that this is the description of a graph. Digraph is a directed graph, and within those outermost braces is all the node information and all the edge information that you need. Okay, so now if I want to see a graphical depiction of what I wrote in the dot file, so this is what I do. So dot minus dpdf minus o text. I'm printing it to a PDF file. I'll just go and try to open the PDF file that I just generated. So here is the PDF file that I just generated. This is your abstract syntax tree. Note that it doesn't have any of those braces and operator size that we had in the parse tree, which are important for the parse tree because it's checking for correctness, but not important here because we already know parse tree has been generated and the program is correct. So just to show you how they compare, yeah, it will be hard, I think. So this is not a very nice depiction of the parse tree, but anyway, here it is. And in comparison, here is the your PDF basically. So, putting them side by side. So do you see the difference? Like, is it visible from the back? Is it visible? You can come to the front if you can see. So basically, for example, the parse tree starts with the node program, but this doesn't start with the node program at all because we don't create a new node, we just show program. We just start with the sequence node, which says that it's a sequence of statements. Then program goes to block, and then block has 3 children, 2 of which are braces over here. So all those things are not there. So a lot of the extraneous information which makes it difficult to read is not present in the abstract syntax tree. Okay. The other thing is that all the names of the nodes in the parse tree are non-terminal names. So these are the non-terminals that appear in the grammar. But in the abstract syntax tree, we don't have to be restricted to using the non-terminal names only. We can use more lucid names which give us the purpose of the particular subtree in a much better way than the parse tree. Okay. Any questions about this? So we'll drop the parse tree from the discussion now and only focus on how to generate the abstract syntax tree. Any questions before we move on? Okay. Yes. Okay, the question is, do we have to take input from the lexer? Yes, all parsers have to do that. So lexer and parser have separate concerns. The lexer just generates the token stream. The parser checks that the token stream is in the right structure. So although something may be a valid token stream, it may not be in the right structure, right? So like for example, if I don't, in an if statement, if I don't use the parentheses around the condition, it will still generate a valid token stream, but it will not be correct syntactically. Okay. So so all this can be moved to the parser in theory. All the token stream detection can, in theory, be moved to the parser because anything can be expressed in regular languages, which is what the lexer uses, can be expressed using grammars also. But it just increases the complexity of the parser. That's why the parts that can be expressed using regular expressions we push to the lexer and just get the final result from the lexer. So yes, to answer your question, you will be getting the tokens from the lexer, but that communication between lexer and parser is already automated in ANTLR. You don't have to implement it, you just get it automatically. Okay. Okay, so let's look at the text, the ANTLR file that was used to generate this particular abstract syntax tree. So So here is the first line says that it's a grammar with the name example2 and it is stored in the example2.g4 file. So those two names must match. The name of the grammar and the name of the file must be the same. Okay. Then I would say ignore this part for now. I would say just look at the production rules for now. Like what are the production rules? So this is a very mini grammar. So for example, program goes to block, that's one production rule. Then block goes to statements, that's another production rules. So how am I getting the production rule? So anything before this colon symbol is a non-terminal on the left hand side. Anything after the colon symbol is the grammar string on the right hand side. Okay. So that's what has happened here. Then if after that there is a certain part in braces, that's actually the syntax directed translation part. That's the action that is associated with that grammar rule. So it's the same thing that we learned in class. It's just the syntax is that it should appear within brace symbols. Like what is the action you want to execute if you had this kind of this node in the parse tree. Okay. Any questions? Okay. So similarly here, block has a single production. I would just ignore the returns part for now, and there's a action associated with that production. Similarly for statements, so this is the left hand side, this is the right hand side. I know I skipped over a few things, I'll talk about them soon. This is the action. Then there is this vertical bar symbol which represents that there is another production rule over here. Okay, and what is the production rule in this case? Can anybody say what is the second production rule for STMTS? Is a null production. So it says that STMTS can also be replaced by the null string. Then there is a associated action with the null production. So null production doesn't always mean that the action will also be null. The action may be non-empty. Then similarly for STMT, here's the left hand side, right hand side, then action, then there's the second rule and action. Then there's a third production rule with STMT also in this case. Okay. Similarly for EXPR, and okay, so here the parser ends at line 114. That everything that was required by the parser has ended here. The rest of the part is actually the lexer part. So typically we had it in a separate lexer file for the first assignment. You can choose to continue with that separate lexer file, that's no problem, or you can also choose to put it in, just concatenate it into the parser file, that's also no problem. Okay. Okay, any questions so far? Okay. So here let's talk a little bit about the actions now. Okay, so to begin with the actions, let's first concentrate on this parser members thing. It says that there is one additional member, an integer variable called count. So this is a global variable. So what is count used for? Count is used for node IDs. So there are nodes in the AST, right? And everybody must have a unique ID to be able to identify them uniquely. So this is the node ID. So I'll just write it in the comment. Please, it's not the ID, it's the AST node counts, like how many nodes have you seen so far? Based on how many nodes you have seen, you assign the ID to the next node. Okay. Now, so program that going to block has a single line action. Can anybody say what this particular action does? Sorry? It's not that hard. It's been printing something, yes. Right. Exactly. So it is printing out a line which says that this is a directed graph called G. Digraph stands for directed graph, and two braces, within which there is something called block.f. Anybody want to guess what is block.f? The what? Yeah. So block.f contains all the text corresponding to that AST graph that needs to go in the dot file. Okay. So dot f is an attribute which contains the text that you need to put in the dot file for a particular subtree. Does that make sense? Okay, so let's try our hand at another one. Let me. So here is block going to STMTS. Okay. What do you think these two statements do? ID equals to stmts.id and f is equal to stmts.f. Ignore the dollar symbols for now. They're just not much meaning to them. So can anybody say what ID equals to stmts.id does? Right. So what is ID? What is the ID field? Can anybody say that? Yeah, let somebody else say. Anybody want to take a stab? What is the .id attribute? So all of these dot something are attributes of some bud. So this stmts.id, here the ID is an attribute of the grammatical symbol stmts, and when it is just ID, that means it's the attribute of the symbol on the left hand side, which is block. Okay. So any clue as to what stmts.id or just ID signifies? Okay. It is actually not exactly a pointer to the subtree. So it is an integer, basically. It's not a pointer. Okay. Node number. Yeah. So exactly that's what it signifies. It signifies the ID of the node, which is kind of an unique identifier of a particular node. Okay. So like what he said, this statement is basically saying that block, the ID of the node for block is same as the ID of the node for STMTS. Okay, why is that the correct thing to do? Right, because we are not creating any new node. So if you remember in the SDT we studied in class, we didn't create a new node when block went to STMTS. We just made block point to the same node as STMTS, same subtree. Okay. Then f is equal to stmts.f. So what is the meaning of this? Wait, let somebody else answer. I think too many people are just sitting passively. So unless people start participating, I'll just start calling upon people randomly. So who wants to answer that f equals to stmts.f? What does it mean? Yes. label of okay. So so dot f, if you remember, here we had something called block dot f. So here we said that block dot f contains all the text that needs to go into the dot file. Okay. So what goes into the docs? Just 1 minute. What goes in dot file? The description of the nodes and edges. Okay. So what do you think stmts.f is? Exactly. So stmts.f is the dot representation of the stmts node terminal. Okay. And when we assign it to block.f, that means we are saying that their dot representations is the one and the same, which is also correct because we haven't created a new node for dot, so it has to be the same. Okay. Any questions about this? Right. So the question is, will there be no node named block in the AST that is generated? No, there will be no node named block. Does it have to be that way? No, it doesn't have to be that way. But here is the convention I have determined, and there is a particular convention that has been specified in your PD2. So that is a convention you have to follow. You had a question? No. So the question is that instead of $f and dot, what if I wrote $block.id or $block.f? Would that be correct? No. So the convention is that when you are referring to the attributes of the symbol on the left hand side, which is block in this case, you just refer to them down. There can be only one symbol on the left hand side. There cannot be any confusion about who it is referring to. Any other questions? Okay. Okay. Now something significantly more complex than what we have seen so far. Okay, so let's go over it one by one. So the production rule here is STMTS going to STMTS followed by STMT. Okay. Now I have renamed this STMTS to S, just to make a distinction who I am referring to and make it clear. So let's go over it line by line. So what does the first line say? Quickly. So $id equals to plus count. What does the first line say? Okay, let somebody from the back answer. Anybody from the back want to try? What does the first line say? STMTS? Yeah. So yes, that's right. So basically count keeps track of how many nodes has been generated, and you just increment count when you are getting a new node and assign the value to ID. Okay. What's the next one? What does the next one do? Is it readable in orange? Maybe I should not make it orange. So, any of you want to try on this side? Yeah, so basically here what is happening is string concatenation. Okay, so there was a dot representation of the subtree of S. There was a dot representation of the subtree of STM, and we just concatenated them. So the nice thing about Java is you don't have to write a lot of code to concatenate strings, right? In C, it's not very, you have to use strcat and whatnot. In Java, if you just write plus, it gives you the answer. So, I mean, we are not going to be using any of the object-oriented features of Java. So that's we'll still be using a C like code, but there are some simplifying things you can do. Okay, so next question again. So who wants to say among you three, what is the meaning of the third line? Sorry. So what does label signify? Exactly. So, so here in the third line, we are generating a string called seq. So it will serve as a label for the new node that you are creating. So we are creating a new node in the first line. If you see that we just said assigned, generated a new node ID. So that is equivalent to generating a new node. And the third line basically says, oh, okay, this will be the label of that particular new node. Okay, so that's great. Anybody want to try the fourth line? So this is basically, I'll tell you the left hand side. Left hand side says that you already have a string. So this $f contains the description of both the subtrees of the children. Okay, so $f already contains that. Now we need to add something to $f. What is being added? So what is the question here really is that what is there in the subtree of the left hand side non-terminal which is not there in the subtree, in the two subtrees of the children? Like what is the additional thing we need to do? Exactly. So there is a new node. So we need to add that particular, the information for that particular new node into the dot representation to get the full subtree for the left hand side non-terminal, which is exactly what we are doing here. Okay, so basically there is just a line. So the line starts with the ID number, which is the node ID, and then it gives the label of that particular ID. So label here in this case should be SEQ. Okay, what's this? What is the meaning of this particular line? So let's not worry about the conditional statement at the moment. Let's just think about what exactly this is. So this is also adding something to $x. That means extending the dot representation with some information. So what is the other information that needs to go into the dot representation of this left hand side thing which is not there yet? So we had the two subtrees. So this second line concatenated the two subtrees of the children. The fourth line added the subtree, added the information about the new node being created. What is the other information that remains to be added? Wait, let somebody else answer. Yeah, but what is it present? It could aspect of the truth. So let me draw it. Probably then it will become clearer. So there was a child, let's say C1. There was a subtree of child C2. We concatenated those two in the first statement. In the second statement, in the fourth statement, we added information about the new root node. Which is this one. These are the label sequence. Let's say what else needs to be added to make it the full subtree that we need. Yes. It needs to be connected. Exactly. These two edges need to be added. So that's exactly what this particular line is doing. It's saying that there is an edge from node ID to node next.id. What is the second? What is the last line saying? Similar thing. Connection to second node, exactly. Why do we need to check this particular thing that the first child may have an ID -1 or not? So in case if it has -1 ID, we're not going to be connecting to it. Otherwise, we are going to be connecting to it. So what does that mean? Right. So, sorry. Right. So this SCMPS has another possibility in which it evaluates to the empty string, in which case it will not have any subtree. So we cannot just connect to an empty subtree and will crash. Basically. Okay. So this is the action for the empty subtree. So what is the, let's get rid of this. So what is happening here in the action for the empty subtree? Exactly. So it is setting its own ID as -1 to signify to others, look, I don't really have a substrate, so don't try connecting to me now. Okay. And the string here, you can set it to a null string or whatever you feel like. Okay. So this should be pretty easy. They are exactly the same thing as we have already seen. So basically, this is statement going to expression. That's the rule. Anybody want to explain? You want to explain the action that is going on here? Okay, so I think that is a pretty succinct explanation that we are generating again a new node, and we are first taking the dot representation of the child, then creating a label for this node, adding the information about this node, and adding the edge from the parent to the child. Okay, so I won't go into everything. I think the rest should be self-explanatory after this. Okay, let's see what I have done for when an expression evaluates to just a number or an identifier. Okay, so so here for both the number and identifier, I'm creating new nodes. Yes. Sorry. Yes, I'll come to that. So for when the expression evaluates to number and identifier, we are still creating a new node, but instead of labeling the node as either number or identifier, we are actually giving the value of that identifier and that number as the labels, just to make it pretty clear what was there. So now the question that he asked, let's see what was, let's, sorry. Yeah, I'll come back. Just one by one. So here is what we generated. Here, let me also open the test case that was there. So here is the test case. So it was a very simple test case, just one statement. And here is the dot file that was generated. Okay. So what are the components of this dot file? So each line of this type represents a single node. So this is node ID 1, node ID 2, node ID 3. This is what? This is an edge between 2 and 3. This is an edge between 2 and 1. So it's extremely simple. The whole the dot language, and there is some attributes for each node. In this case, we have used labels. You can use color or whatever suits your fancy. There's a lot of options you can use. But for my purpose, I only use the label attribute with each particular node. So, any questions about the dot format? Right. So, what do the system.out.printlns do? So, for example, here, this system.out.println prints this digraph with braces and then the dot description of the entire subject. Those are just for debugging that I had added. No. So let's see. Okay, so here is what we got in the dot file. Okay, now what I did is you can directly write your output to a file. I didn't do that. I kept it even simpler. This is what I did. So here, let's see up here. Okay, here, instead of directing the output to a file within the ANTLR program, here I'm directing the output to this test.dot at the command line. So it will have the same effect, but it will require you to write less code. Basically. Otherwise, you have to open the file, write in it, close it, all within the ANTLR program. But if you redirect the output at the command line to the dot file, you don't have to write all that code. But it's personal preference. I don't want to force you to do one way or the other, and output gets redirected and it's done. Okay. Okay. Any questions about this? Okay. So any other questions about the demo that you want to see some other features or something else being done? Because this is significantly more complex than the last PD1. So make sure that you understand it, what is going on here, and it will be even more complex in the next two PDs. So make sure that you understand it very well. Yes. Parse tree and AST simultaneously, yes. Okay. Let me try. So this is the parse tree. Let me. Okay. So the problem is that the PNG viewer didn't do a great job on this. So where did the past tree go? Okay, so I can show you. The thing is that I'm not being able to put them on the same screen. So if somebody can help me itself is pretty bad. So I can show you what happened last time. Okay. Yeah, so this is what is happening. This is okay. What kind of document? I'm not. Okay, this is the PNG. Okay, so now I think it should work. Okay. Um, okay, so that is kind of okay. Is this visible now? I think this should be better. Okay. Yeah. So what was the question? Okay. So basically here you have this, for example, the assignment statement, and here it's just represented as assignment. So one more thing I want to show you is this. So we talked about ambiguity in class, right? So I did say in class that you can use associativity and precedence to break ambiguity in grammars. So there is ambiguity in this particular grammar too that I'm using. So for example, what is the precedence among the different arithmetic operators? What is the associativity of each of the arithmetic operators? So here, for example, I have said that the associativity of the addition arithmetic operator is plus. So ANTLR already has an inbuilt default system of precedence and associativity. If the precedence and associativity that you want, if it matches the default system, you don't have to write a single line. But if you wanted to do something else, it's worth knowing how to do it. So here you can write associativity equals to right, or associativity equals to left, to show what is the associativity. Then precedence can also be done. So precedence basically is determined by the relative positioning of the rules. So for example, if I have used this equal to and plus sign, and I want to give equal to a higher precedence, so I have placed the rule involving the assignment expression above the addition expression. So that's how I have indicated to the grammar that I want equal to be at a higher precedence than addition. And this is why in the test case where we had equal to and then plus, the equal to was evaluated first, then the plus was evaluated. So this is opposite to what we expect, right? So if you see the, let's see what is, if you see the parse tree, the equal to is evaluated first, then the plus is evaluated. Okay. we can make it do the opposite thing by changing the order of those two grammar rules. Okay. So why is equal to even being considered as an operator? Can anybody say why is equal to an operator? I mean, plus minus are operators that we all know, but equal to is equal to is its assignment. Why is it being considered as an operator? Right. So for whatever reason, uh, equal to is considered as an operator because you can have statements of this form: x equals to y equals to z. In this case, y equals to z will be evaluated first, typically, and the result of y equals to z will be same as the value of z. So y equal to z is not only a task; it also has a return value. That's why equal to is an operator. Okay. So it returns the value on the right hand side of the equal to, which then can be used by some other expressions. Okay. So I'll just show you what happens if I change the order of things. Sorry? Oh, okay. Did I not give that? Yes. Okay, so as you can see, the parts tree has changed. Now the equal to has moved up, plus has moved down. Okay, so and if I try to get a new AST, first let me close this. Minus. So this assignment node has moved much higher in the AST just by changing the precedence of the rules. Okay, so there was another question: what does returns mean? Okay, so returns basically says like what are the attributes that a particular grammar symbol exports to other grammar symbols, like which attributes of this particular grammar symbols can others use. So if expression returns id and f, then you somewhere else you can use expression.id and expression.f. That's what returns mean. There may be other variables that the actions compute, but if they're not being returned, those variables will not be available outside of the local action. So that's what it is. Any other questions? Yes. Okay, so the advantage of AST is that it is more oriented for analysis. Parse tree is more for checking that the particular test case matches the given grammar or not. That's the purpose of parse tree. AST has a lot more information that is relevant to analysis and a lot less information that is relevant to checking. I mean, you cannot check by using an AST, you cannot check if the program was correct or not. However, if you wanted to perform a particular analysis on the structure of the program and let's say convert it to something or apply some optimization, AST offers a much faster way to do it. Okay, so for example, excuse me. Let's see, where is it? So for example, here, at this node in the AST, you immediately know that the statement below this is an assignment statement. Okay. You won't get this information in a parse tree. In the parse tree, you will have to examine all the children and get the understanding, oh, this was an assignment statement. You may not be even able to understand that this was an assignment statement just by looking at the children. You may have to go several levels down to get the understanding, okay, this is an assignment statement. AST really tells this is an assignment statement. So parse tree is used for making sure that the program is syntactically correct. If you can generate a correct parse tree out of a program, that means that the program is syntactically correct. AST is generated when you are pretty sure the program is correct. Okay, so there's no syntax checking going on anymore. Now you want to do some analysis. Maybe you have, let's say, you have a special hardware operation in your machine. We optimize the assignment statements. We gives you a lot of speed on assignment statements. So you can very quickly find the assignment statement and replace them and generate the correct code for them using an AST. You can do the same thing first. I'm not saying you can't do it, but it will take a lot longer, a lot more analysis. Sorry? Oh, okay. How is that's a good question. So, the question is, how is the AST information delivered to the rest of the compiler phases? Is that the question? No. So, why? First of all, why is AST required during compile time? AST is not strictly required if your only goal is to convert from high-level language to machine language. AST is not strictly required. However, if you want to do more intelligent optimization, like the example I gave you, you need the AST to do it in a fast manner. Okay. So I think we need to discuss some more concrete examples, which we'll do in the next class, like exactly how to do, what to do with AST. But for now, I'll just say that it is used a lot in doing analysis of the program structure, and if you wanted to do some optimization based on the program structure, if you wanted to use some special hardware features based on the program structure, you want to use an AST. Another good use of AST is if you wanted to convert from one high-level language to another high-level language. AST is very, very easy and flexible tool for converting. Let's say you wrote something in C, you want to convert it to, I don't know, maybe R. You want to write an R program. AST is a much faster way to do it. It gives you only the relevant syntactic information. It doesn't give you a lot of other things. It gives it the information to you much faster. The information is at higher levels rather than having to go and check all the children and make a decision on this and then just get the information. Right? It's not an integral component, but it's a very important compiler concept. Everybody who is learning compiler should know what is an AST and how to generate it. Okay. Yes. if you have left recursion typically just by itself is not a problem. Okay, so it depends on exactly what is causing your error. If you just have left recursion, not like guaranteed that you get an error. So you need to look into it in more detail, like what is going on. So the reason, so the question was, if there is a left recursion in the grammar, will the parser go into an infinite loop? The answer is no, it won't. We haven't studied the parser algorithms, but when we study it, we'll see that parsers are very much capable of handling left recursion in grammar. Any other questions? Yes, any other questions? How do we have to start with any question? First, you should download the question paper. I don't know what you should do first. I don't know. So yeah, I will be uploading this example grammar file to the backpack. So my recommendation for executing the PD2 in a low effort and less frustrating manner would be the recommendation that is given for any significant software project. Try to break it up into levels. Don't try to do the entire PD2 all at once. Try to break it up into levels. Make sure each level works. You will finish much faster that way. So you should first check that it probably works. If there are no statements, you're still able to get a single node AST. Get the best case working, then add some more grammar rules and make sure that that works. Just keep going in that way until you reach as much as you can. Any other questions? Okay. So I think that's it.